Hello friends, today we discuss inverse Laplace transform. So we already told you that what is the application of inverse Laplace transform. So sometimes to solve very complicated differential equation, normally we cannot solve them. So we use Laplace transform. We convert this differential equation to simpler one, solve them, and via inverse Laplace transform again we go back to the previous mm, position and get the previous problem, and we get the solution of this type of complicated differential equation. So in this way, this is important. So now start. So let f be a real valued function, capital F be a real valued function of the real variable t, defined for t greater than 0. Laplace, if Laplace transform capital F t equal to fs, this we already defined like this. So then then ft, this ft is called the inverse Laplace transform of the small fs. That is L inverse of fs. So you are just taking this L, taking this side as an inverse. This comes as a like this. So L inverse of fs becomes ft. See examples. So since Laplace transform of e to the power at is equal to 1 by s minus a, so L inverse of 1 by s minus a will be e to the power at. So just like this L goes this side and becomes L inverse. There is another example. You can see this. Laplace transform of cos 2t is equal to s by s square plus 4. Therefore, Laplace inverse of s by s square plus 4 equal to cos 2t. Now we state a theorem. We would not going to prove this. The theorem says existence and uniqueness of the inverse Laplace theorem. Inverse Laplace transform. So in the cases where uh, inverse of a transformation is exist. So what is the key statement here? So let f1t and f2t be two continuous functions for t greater than 0 having the same Laplace transform fs. So two functions f1t and f2t both have the same Laplace transform. That is L of f1t is equal to fs and L of f2t also equal to fs. So if this kind of thing holds, if this kind of things holds, then we can say L inverse of fs equal to f1t and L inverse fs equal to f2t. They are same, and in that case L1t equal to f2t. F1 sorry f1t equal to f2t. So for a particular given function fs, their given function is fs. It has always a unique inverse Laplace transform. It is not possible that you are getting two different functions. For example, sometimes one can say that for integration, suppose you are given a full function. If you take an integration of x dx, so in that case you get many inverse, because integration of x is x square by 2 plus constant. So if we change this constant, then this always change. Now some elementary Laplace transform. These formulas we already know from the previous discussions, because these are the just inverse of those formulas. So since uh, Laplace transform of 1 is 1 by s, Laplace inverse of 1 by s is equal to a 1. Since Laplace transform of t to the power n equal to gamma n plus 1 by s to the power n plus 1. So Laplace inverse of gamma n plus 1 by s to the power n plus 1 equal to t to the power n. And so on. I am writing these formulas. You can pause and see these formulas. So there is nothing to prove these formulas. You already see. Now check some examples. Find the values of the following. Laplace inverse of 5040 divided by s to the power 8. So this 5040 can be written as 7 factorial divided by s to the power 7 plus 1. So look, this is the Laplace transform of t to the power 7. So Laplace inverse of this term is will be t to the power 7. Similarly, Laplace transform 1 by s plus 5. So this can be written as Laplace inverse of 1 by s minus of minus 5. So this is equal to e to the power minus 5t, because we know that the Laplace transform of e to the power at is given by s 1 by s minus t from that formula. This. And Laplace inverse of s by a square plus 16 is equal to Laplace inverse of s by, this can be written as a square by 4 square. So therefore, this is equal to cos 4t. This is the formula for, this is the Laplace transform for cos 4t. So Laplace inverse of this is equal to cos 4t. Okay, next another theorem, linearity of the inverse Laplace transform. So this again, this formula comes from the linearity property of the Laplace transform, very similar to that. What is this statement? It says that if ft and gt be any functions of t for t greater than 0, such that Laplace transform of ft equal to small fs and Laplace transform of gt equal to small gs, and a be any constant, then Laplace inverse of afs plus bgs equal to this, act as a linear. So this a comes out, this b will be comes out, and this summation distribute. So this becomes a times L inverse of fs plus b times L inverse of gs. So proof. So as we know that Laplace transform of ft equal to fs and Laplace transform gt equal to gs. So therefore we can write, we are starting from this point. So write this thing afs plus bgs. It can be written as a. So fs can be written as Laplace transform of ft and gs can be written as Laplace transform of gt by definition. Already it is given here. So Laplace transform is linear, so I can take this sum inside and add them together and we get this. So this becomes Laplace transform AFT plus BGT. Now we can take this Laplace transform this side as an inverse. So Laplace inverse of this AFS plus BGS can be written as AFT plus BGT. Again, what is FT? FT is the Laplace inverse of small fs and GT is the Laplace inverse of small gs. So in this way you can prove this. Now see some example. So this is a, we need to find this inverse of this Laplace inverse of this function. So we, since it is a linear, we can break this out. So this term can be written as L inverse of 1 by s plus 3, L inverse of 2 by s plus 5, and L inverse of 6 can be written as factorial 3. So we know that factorial 3 is equal to 6. So now apply formula. So what is the Laplace inverse of 1 by s plus 3? This would be e to the minus 3. And what is the Laplace transform s plus 5? It will be e to the minus 5t, and this 2 comes out by the linearity property. So 2 times e to the minus 5t, and this becomes a t cube. This is the formula for. So there is a similar type of exercise. You can try to solve this. Uh, there is another example, little different. L inverse of 2s minus 5 by 4 a square plus 225. So first we break this. So 2s minus 5, 4 square plus divided 24. We all the formulas involve that s and everywhere here s square and something like that. There are no coefficient was there. So we want to remove those coefficients. So we just taking out this 2, taking out. So taking 2 taking out from the numerator. So we get 2 times s minus 5 by 2. And in the denominator, we taking out 4. So it's become a square plus 25 by 4. Now this becomes 1 by 2. And we can write this is equal to this first term we can break this. We can break this in, so this can be written as s by a square plus 25 by 4. Half is there. Here is a 5 by 2 and minus is there, so therefore we get a minus here. So 5 by 2. This 5 by 2 can be, you can write here also, no problem for that. Later I have done here is 5 by 2. So, and a square plus 25 by 4 here. So this is equal to half a square, and 25 by 4 can be written as 5 by 2 square. Similarly, 1 by 2, taking 5 by 2, writing 5 by 2 here, and a square plus 5 by 2 whole square. Now we can use directly the Laplace inverse. So, I like to put everywhere this Laplace inverse term here. So everywhere there will be Laplace inverse here. So maybe not here. So at least if we maybe I can write this like A inverse is 2s minus 5 divided by 4a square plus 25, and there is a half. There is, you can take Laplace transform here. You can take Laplace transform here, everywhere. Now apply this. So this is a formula for cos. So cos, and this a is 5 by 2. So cos 5 by 2 t minus half sine 5 by 2 t. Similar way you can try to solve this. This is another exercise for you. Similar type of exercise. Now we want to find an analogous to the first shifting property in the Laplace transform, inverse Laplace transform. So this is a very useful formula again. So by the first shifting theorem of Laplace transform, we have L of f, if L of ft is equal to fs, then L of e to the power at ft is equal to f of s minus a. Therefore, we can say if L inverse of f is equal to ft, then L inverse of f of s minus a will be e to the power at ft. So this is a useful formula. You can take this as a working rule, this formula, and using this formula, you can directly obtain following formula. You can see and verify. Already we have done this proof of these formulas. We derived this formula in the previous chapters. So you can use those formulas also. You can directly verify these formulas. These are simple, very simple formulas. Now try to solve some example. So find Laplace inverse of 12 by s minus 4. So look here, this is becomes a s minus 4. So there is a shifting is going on. Whenever we replace s by s minus 4, there is a shifting on shifting by 4. So whenever there is a shifting that by a, some e to the power at will be comes out. So how can I find this? So write this L inverse of 12 by s minus 4 whole cube is equal to L inverse. This can be written as 6 into factorial 2. Why factorial 2? Because here, look, this formula. We are using this formula. If you see the above, so here is this formula. So this is already t to the power n form. This is s minus a to the power n plus 1 form. So use this formula. So e to the power at will comes out and t to the power n. So if you use this, so this 6 will be comes out, and we write it like 2 factorial 2 by s minus 4 whole cube. Now this becomes a t to the power n type formula, and here is the shifting by 4. So e to the power 40 comes out, and this is looks like a t square, because factorial 2 here, this 3 can be written as 2 plus 1. So t6 e to the power 40 t square. So there is a similar type of exercise, another exercise. You just try to do yourself first. I already give you the solution, but try to solve this yourself and check with the solution. Also, I'll give you two more examples. Try to solve these as an exercise. You can try to solve. Next day, we will see some more properties of the inverse Laplace transform.